Exercise 23.13 is exploring the Gabriel synthesis using it in the context of a multi-step synthesis. So if you look at the molecules given to you in A, if you look at those molecules, and let me actually do this, these, you are trying to turn an alkane into an amine. So you can read this two ways. You can start with the alkane and think about how you can turn that into the amine, or you can look at the amine and think about how do I know how to make an amine and go in the other direction. If you go in the other direction, if you start with the amine and think how do I know how to make an amine, that's where the Gabriel synthesis would come in. We know that to make an amine with the Gabriel synthesis, you use this recipe that we sort of devised in the video on the concepts and mechanism of the Gabriel synthesis. Now, you always start with phthalimide. You always have potassium hydroxide to turn this nitrogen into a nucleophile. Then you always have an alkyl halide, and as a last step, you always add either hydronium or hydrazine. Either one would work. In this example, we have to figure out what the alkyl halide is going to be. Oops. So we can take our phthalimide, we can take these reagents, and we have to think about what we want our alkyl halide to be. So we'll take the amine that we have, and just like we did in the previous video, you can replace the nitrogen on the amine, just erase it, and replace it with a leaving group. So for example, bromine. And actually, let me do this in green. Chlorine or iodine would work just as well. And the result of that is that we would get our final product. So if we had those molecules, then we would get the amine that we want. We would treat phthalimide with potassium hydroxide. That would rip this hydrogen off, turn the nitrogen into a nucleophile. Then that could do an SN2 reaction, kick the bromine off. You'd have the bond between the nitrogen and the carbon, and you'd release the nitrogen from phthalimide by doing a hydrolysis, either acid-catalyzed hydrolysis with hydronium or a nucleophilic acyl substitution with hydrazine. Either way. But in order to do this reaction, the carbon chain that we need is this alkyl halide here. And so our exercise, or this synthesis, becomes a slightly different question. How can we get from this alkane to this alkyl halide? Okay. Now, how can we do that? Because once we have this, we can use the Gabriel synthesis to get the final amine that we want. Well, a key thing you should notice here is that you have an alkane to start with. There are very few reactions you can do with alkanes. Look at them. You don't have any nucleophiles there. You don't have any electrophiles. Carbon and hydrogen have almost the same electronegativity. Carbon is ever so slightly more electronegative. But the bonds, the electronegativity is not, the difference is not big enough to make any partial charges on that molecule. There are no pi bonds, so there's no extra electrons there, no extra molecular glue. So this is not a particularly reactive molecule, an alkane. There are really two reactions you can do with alkanes. The first one is you can light it on fire and turn it into carbon dioxide and energy. That's combustion. That's not going to get us this molecule here. So the other one is the one that we know we have to use. The other one is adding on a halogen using a radical. So the radical we've been used to using this semester has been NBS, N-bromosuccinimide, and you were introduced to that for the first time at the end of Organic Chemistry 1, and you need to use that in the presence of ultraviolet light. We've talked about the mechanism that happens, that uses several times this semester, and also, if you're interested, I can send you videos that I made for Organic Chemistry 1 that walk through that mechanism in great detail. For this exercise, what you'd want to know is that NBS and light, N-bromosuccinimide, in the presence of ultraviolet light, adds a bromine onto the most substituted carbon in a molecule. Excuse me. And so here we have primary carbons, carbons that are only bonded to one other carbon, and we have tertiary carbons, carbons that are bonded to 3 other carbons. And so the tertiary carbons are the more substituted ones, and that's where the bromine adds. The halogens are windows to the world. When you have a halogen on a molecule, you have a good leaving group. And with a good leaving group, you can do substitution, you can do elimination. If you do elimination, that creates a pi bond, and then you can do addition and add things onto the pi bond. Really, all the reactions you've learned are open to you once you have a halogen. If you compare what we have here with the molecule we want, you'll notice that the bromine goes away. In other words, we have to eliminate it from the molecule. Elimination reactions were discussed at length in Organic Chemistry 1, and I can send you a bunch of videos for those. The general idea is that the carbon that has the leaving group on it is called, in this context, the alpha carbon. This is very different from the alpha carbon next to a carbonyl. It's confusing because they both are called alpha carbons, but they mean something completely different, and they have a completely different chemistry. In the context of elimination reactions, the alpha carbon is the carbon bonded to the leaving group, and every carbon bonded to the alpha carbon is a beta carbon. So here there are 3 beta carbons. You'll notice that there's a symmetry in this molecule. The top and the bottom are really symmetrical, and so I'm going to erase this bottom one because it's really the same. You would end up getting the same product as in the top one. Now the beta carbons are important because in an elimination reaction, a base comes in and steals one of the beta hydrogens. So there's a hydrogen on this beta carbon, there's a hydrogen on this beta carbon. Those are called beta hydrogens. And those get stolen by a base. Now you could have 2 types of bases. You could have a skinny base, something like sodium methoxide, or you could have a bulky base. That would be something like potassium tert-butoxide. And these are bases that you would definitely want to know. Sodium methoxide, the oxygen there has a full negative charge. The ET stands for an ethyl group. So it's really this that's acting as the base. The sodium is just there as a counterion. You could see that this is not a very big carbon tail. That would be able to wiggle its way into very crowded spaces. Potassium tert-butoxide is a bulky base. The tert-butyl group looks a little bit like a chicken's foot. And then it's bonded to an oxygen. And that oxygen, the negative charge on it is being stabilized by the positive charge on the potassium. So this is the tert-butyl group, and then you have the oxygen and the potassium. You'll notice that this tert-butyl group is always used to illustrate the effect of crowding. Whenever crowding is important, they'll use the tert-butyl group to illustrate the difference that crowding makes. Because this tail, this tert-butyl tail, is so crowded, this base will only be able to steal hydrogens that are not in crowded environments. So, if you think about the alkyl halide that we have here, and the 2 beta hydrogens that could get stolen, you'll notice that one of them is crowded. If you want to think about it very precisely, this beta carbon is tertiary. It's bonded to 1, 2, 3 other carbons. It's crowded. The other beta hydrogen is not very crowded. The carbon that it's attached to is just bonded to 1 other carbon. It is primary. So you can use different types of bases to prefer each of those types of hydrogens, each of those environments that the hydrogens are in. If you have a skinny base, like sodium methoxide, or sodium methoxide, or sodium hydroxide, if you have a skinny base, then it will attack the carbon in the more crowded position. It's able to wiggle its way through there, steal that hydrogen, the electrons go toward the leaving group and kick the leaving group off. And what you end up with in that case is a pi bond going between the alpha carbon and the beta carbon that the hydrogen was stolen from. On the other hand, if you have a bulky base, like potassium tert butoxide, the bulky base won't be able to reach the more crowded beta hydrogen. It will steal the less crowded beta hydrogen. The electrons will still go toward the leaving group and kick the leaving group off. So you still form a pi bond, but now it's between the alpha carbon and the beta carbon whose hydrogen was stolen. Oops. These two. Okay, so these are the two possible elimination products that we can make. When we compared the molecule we had that had a bromine here to the molecule we wanted that didn't have a bromine, we knew we needed to do an elimination reaction. But what type of base should we use? A skinny base like sodium ethoxide or a bulky base like potassium tert butoxide? Well, that depends where we want to move the reactive part of the molecule. Do we want it to move it toward the middle of the molecule or toward the end? And when we see the bromine on the end, it becomes clear that we want the reactive part of the molecule to go toward where we want to put the bromine. So that we want this alkene here. We want to do an elimination reaction toward the less crowded carbon. There were a couple key words that are important. They'll come back later in this chapter to illustrate the difference between these two alkenes. One of the alkenes, if you think about how many carbon chains are attached to the carbons in the double bond, one of them has 1, 2, 3, 4 carbons attached. And so that would be described as being tetra-substituted. The other alkene, if you think about the carbons in the double bond, that has 1, 2 carbons attached to the carbons in the double bond. So that would be described as di-substituted. And there were technical terms for the more substituted and the less substituted products of an elimination reaction. The more substituted product, here the tetra-substituted product, was called the Zaitsev product. The less substituted product, here the di-substituted product, was called the Hofmann product. Here we want the Hofmann product, and to get that you use a bulky base like potassium tert butoxide. So I'm going to take this setup that we have here, and I'm going to fill that idea in. So the only thing we could do with an alkane, a pure hydrocarbon, was to do a radical reaction. We could have also lit it on fire and turned it into carbon dioxide, but that wouldn't have gotten us closer to our product. So we used N-bromosuccinimide in the presence of ultraviolet light, and that put a bromine on the most substituted carbon in that carbon chain. So a bromine here. Then we just determined that if we used a bulky base like potassium tert butoxide, TBUOK, that will do an elimination reaction toward the less crowded carbon. In other words, we'd form a pi bond toward the carbon where the bromine is attached. So now we just have to think about how we can get this alkene that we have now to that alkene with the bromine that we want there. And what you'll notice is you start with a pi bond and a molecule that does not have a bromine on it, and in the end, the pi bond goes away, and you use that extra molecular glue to add a bromine, and what may be a little harder to see is a hydrogen on. After all, this carbon here does not have any hydrogens on it, but this one has one. So we've added both a hydrogen and a bromine onto that molecule. That's an addition reaction, and specifically, it's hydrohalogenation, HBr, one of the first addition reactions you learned in Organic Chemistry 1. You might remember, though, that HBr all by itself is Markovnikov addition. In other words, if you just add HBr by itself, the hydrogen would go to the less substituted carbon. But here, the hydrogen has gone to the more substituted carbon. This carbon here is bonded to 1, 2, 3 carbons, so it is tertiary. And the carbon that the bromine attached to is only bonded to one other carbon, so it is primary. Notice that the hydrogen went to the more substituted carbon. That is anti-Markovnikov addition. And to get anti-Markovnikov addition, you have to include peroxides. And that's a reaction that was discussed at length in Organic Chemistry 1. So ultimately, you can use 3 steps to get a bromine on this end carbon there. You can use N-bromosuccinimide in the presence of ultraviolet light. That attaches a bromine onto the most substituted carbon. We want the bromine on a different carbon, so we have to move it. We can take this bromine off by doing an elimination reaction. We want the electrons to go toward where the bromine should attach. That means getting the less substituted alkene, the Hoffman product, so we use a bulky base, potassium tert-butoxide. Then we want to do anti-Markovnikov addition of H and Br, so we use HBr in the presence of peroxides. Now this is a lot of review from Organic Chemistry 1, so if you don't feel comfortable with any of these reactions, let me know and I can send you videos that go into detail about how all of these work, both in terms of the mechanisms for all these reactions and the conceptual explanations behind them. They were whole chapters in Organic Chemistry 1. Well, once we have that haloalkane, we can take the synthesis that we know to turn a haloalkane into an amine, the Gabriel synthesis, and that gives us our full synthesis. So, once we have this haloalkane, we can take phthalimide, turn it into a nucleophile with potassium hydroxide, and then take that haloalkane, have the nitrogen in phthalimide do an SN2 reaction with it, and then hydrolyze the nitrogen from the phthalimide, and we'll have our product. Overall, the recipe for this reaction would be to take, our alkane, treat it first with N-bromosuccinimide and light. Second, so that will give us this haloalkane. Second, a bulky base like potassium tert-butoxide. That will do an elimination reaction toward the less crowded beta carbon, the Hoffman product. Then, we'll treat this with HBr in the presence of peroxides. That will add the hydrogen on the more substituted carbon and the bromine on the less substituted carbon, anti-Markovnikov addition. Once we have that, we can take phthalimide treat it with potassium hydroxide, and those will react with our alkyl halide that we've made by this point, and then hydrolyze it. We could either use hydronium, or you could use hydrazine. And that final step would give you the amine through the Gabriel synthesis. So in this exercise, in this first step here, or this first part of this exercise, we used reactions from all throughout organic chemistry in order to turn an alkane into an amine, and to be really selective about where the amine was forming. Okay, let's try another one. Here, we have a carboxylic acid, and we want to turn it into an amine. And the exercise is asking us to use the Gabriel synthesis for this. So we can take our general recipe for the Gabriel synthesis and just switch the appropriate alkyl halide in. So we know we can use the Gabriel synthesis to create an amine. The specific amine that we want here is this amine given in the products. To make that, all we have to do is use an alkyl halide where the nitrogen is replaced by a leaving group. So that could be chlorine, bromine, iodine. Any leaving group would do. So if we had this alkyl halide, we would be able to make this amine using the Gabriel synthesis. The question is, or let's actually use bromine here. Chlorine would actually work, but it would be a slightly different series of steps that we're going to use. So if we had this alkyl bromide, then we would be able to make this amine. The question is, how can we turn the carboxylic acid they gave us into that alkyl bromide? How can we take this molecule and turn it into this one? Because once we do that, we're home free. We just use the Gabriel synthesis. But how do we do that? Okay. Well, the first thing we have to do is get rid of bonds to oxygen. You'll see there are 3 bonds to oxygen here. That's really oxidated. And there are no bonds to oxygen here. So we can do a reduction to reduce the number of bonds to oxygen. We could treat this with excess lithium aluminum hydride, a strong reducing agent, and you always follow that up with a water wash to stabilize any charges that form. The result of that step is that you would turn the carboxylic acid into an alcohol. You'd replace 2 of the bonds to oxygen with bonds to hydrogen. Okay, but we still don't have the bromine. We need to replace this alcohol with a bromine. You may or may not remember the reagent that lets that happen. We've used it this semester, but not very often. It's phosphorus tribromide, PBr3. The way that it works is that the alcohol attacks the phosphorus. In this atom, the phosphorus is bonded to 3 electronegative atoms, the bromines. And so the bromines steal electron density, becomes slightly negative, and the phosphorus is slightly positive. So this oxygen here will attack that phosphorus and kick one of the bromines off in an SN2 reaction. When that happens, you have 2 things. First, this bromine is gone. It's separated, it's on its own. It's a bromide ion, so it has a full negative charge. That's the first thing. And the second thing is this oxygen is now going to be bonded to the phosphorus. Let me actually move this one bromine to the other side. So we will have this here. Notice that the oxygen now has 3 bonds, and that gives it a full positive charge. What you have here is a good leaving group, and so all you need is a small nudge from a nucleophile, and bromine is able to act as that nucleophile. It swoops in, attacks this carbon, kicks this whole big thing off. And the result is that we have the original molecule, but the oxygen has left. This whole big group acts as a leaving group and ends up like that. and in its place, the bromine nucleophile steps in. So notice that the overall effect of PBr3 is that it replaces an OH with a bromine. And it does it with just really two successive SN2 reactions. You have an SN2 reaction up here, where the oxygen nucleophile attacks the phosphorus and kicks the bromine leaving group off, and an SN2 reaction here, where the bromine attacks this carbon and kicks this weird oxygen leaving group off. So we can get the alkyl halide that we wanted by first reducing the carboxylic acid to get the alcohol, and then replacing the OH on the alcohol with a leaving group like bromine using PBr3. I put chlorine there at first. If you had used chlorine, if you wanted to make it chlorine, the way to turn an alcohol into a chlorine, an OH into a Cl, is to use thionyl chloride, SOCl2. So SOCl2 is kind of like the chlorine version of PBr3. But the mechanism for that is a little longer, so I thought I would use the PBr3 so that I could show you how it's working. Same idea though, the thionyl chloride ends up turning the oxygen of the alcohol into a good leaving group. So we have an idea for our synthesis. We can take our carboxylic acid and first use excess lithium aluminum hydride, followed by a water wash to turn the carboxylic acid into an alcohol. Then we can treat the alcohol with PBr3, phosphorus tribromide, to get the bromide. And once we have that, we can use phthalimide in the presence of potassium hydroxide followed by the alkyl halide that we wanted, that we have at this point, so this is already there, and then finish that off with either hydronium or hydrazine. And what we achieve is we turn the carboxylic acid into an amine. So we reduce it to the alcohol in these two steps. We change the alcohol into an alkyl halide in this third step. And the fourth and fifth steps are the Gabriel synthesis that turns the alkyl halide into a primary amine. So in these examples, we've explored a couple ways that you can include the Gabriel synthesis in multi-step syntheses that are based on the reactions that you've learned in the last year, in the last 2 semesters in your organic chemistry course.